Okay, so today I'm going to continue. We're going to continue torturing this multiple server queue, and the first the model I'm going to look at is the idea of different server efficiencies, and then time permitting, I'm going to talk a little bit about array states and index property change events. Again, they've been touched on, but I'm going to go into them a little bit more deeply. So let's get a pen going here. Red. Okay, so here's the idea of this. It's our regular multiple server queue idea. But up until now, we've had, well, in our very first model, we were simply counting the number of available servers, and we were just simply counting the number of customers in the queue. What we're doing for this model is adding the idea that each server, now we're going to model the servers explicitly. So instead of just counting the servers, we're going to treat them as individuals. And what makes one server different than another? Well, in this case, each server is going to have an efficiency. In other words, based on either their skill or their training or their experience, each server is going to be either faster or slower than, quote, normal. And on top of that, we're also going to count treat each customer as a unique thing. And they're going to carry their processing time along with them. So instead of having the queue specify what the processing time, which a number of our models have, the idea is that now each customer is going to carry their processing time along with them. What this allows for is the possibility that we may have different customers having different processing times. Well, I mean, each customer will have a different processing time, but we could have customers that have processing times that are generated from a different distribution. And again, one way to think of that is, for example, like if you look around the supermarket, there are generally 3 categories of customers in a supermarket. Okay, one is one that's pushing a cart. Another type is carrying a little hand basket. And then the third doesn't have any. They're just kind of picking things up and holding them in their hands. And if you think about it, if you look at the probability distribution, if you were to try to construct a distribution of how long it takes for a given customer to check out, they would be different depending on whether they're pushing a cart or holding a basket or just holding them in their hands. I mean, on average, customers pushing a cart would have a longer processing time because in general they would have, why? Because they would have more items. So even if each item is just a quick swipe on the barcode scan, if you have more items, it's going to take longer. And on the other hand, if you're just carrying your items in a small basket, then you can't carry as much items. So again, on average, your processing time for a customer carrying a basket is going to be less than a customer pushing a cart.
Arnie, so like the assumption is that every customer carrying a basket has a specific time and every customer with a cart has a specific time. I guess like there's one time for customers with baskets, one time with customers with carts, not each customer has their own time. Like 5 seconds for customer 1 with basket, 6 seconds for customer 2 with basket, 10 seconds with customer 1 with cart.
Well, let me ask you, is what you just said, is that going to be a reasonable, realistic assumption?
I mean, I think that it's reasonable to think their times would be different, but I think if you are building a model, I don't know if that's possible.
Well, I mean, everything is possible in building a model. My question is, if you're saying every customer of a given type has exactly, say, 10 seconds of their processing time, is that going to be a realistic assumption to make? I mean, are you
No,
comfortable
no,
with that?
no. I don't
Yeah,
think
no, yeah, yeah, and you shouldn't be. You know why? Because even, yeah, and again, keep in mind that the supermarket customer it's a metaphor. It's just an analogy. I'm not literally talking here. However, if you think about that as a metaphor, even customers pushing a cart are going to have different quantities of items in their cart, and that means that if the time to check out is a function of how many items you have in your cart, then every customer is going to have a different number of items in their cart. And and furthermore, if you're looking at it from contrasting the cart versus the handbasket, there could be situations where somebody in a cart only has a few items and someone with a hand basket has more, in some cases. The point is that in these models, if you make things too deterministic, then the models lose their power. In other words, if every customer, even customers of a given type, have exactly the same processing time, then you're not going to capture the kind of randomness that you encounter in the real situation. So for this model, though, I mean, the idea is just that the customer is going to come in with their processing time instead of having the server be dictating the processing time. Now, in this particular case, though, the actual processing time is going to be a function of both the customer and the server. Because if a customer comes up and they're going to have what their processing time is this is how long it would normally take to process this particular customer. But if the server's efficiency is going to come into play with that, because if you have a faster server, they're going to be able to process the same customer faster than a slower server. And that's what we're trying to capture. In other words, again, going back to this whole idea of iterative modeling, we observe our system. And in the previous models, each server was basically homogeneous. Even when we had two types of servers in some of the previous models, each type of server was homogeneous. And what we're doing here with this model is every server is completely different. In other words, when we observe our servers, and we notice that for tasks of about the same amount of work, some servers are faster than others. And we want to take that into account. Why? Because that may be one of the things that we can control or affect if we want to improve our performance measures. In other words, what is it that can improve a server's efficiency? Well, actually, a lot of things, one of which is training, another of which is sort of examining the nature of the task. And this kind of gets into, industrial engineering types of things where, okay, how is this task being performed? Is there a more efficient way of doing that? And figuring out what that is. Again, there are a lot of different ways of doing it. Like if we're talking about machines, we could talk about maybe either upgrading them or performing more regular maintenance if it's the wear and tear that's making them run a little slower. The point is that now we have our models up to now haven't captured that, because the servers were just kind of treated as being homogeneous. And now our servers are going to be heterogeneous. And our customers could be heterogeneous as well. I mean, in this particular, for this particular case, they're not. But towards the end, I'll show a way that we could make them a little more heterogeneous. Okay, so now, instead of just saying, like in our previous models, when we said, okay, now we're going to start service, we need to schedule an end service, and the delay time in that is the time it takes to process that particular customer. Now we're saying, okay, the customer is going to have their processing time, but we're going to multiply it by the server's efficiency. So basically, if the server's efficiency is less than 1, it means they're going to go faster than normal. And if it's greater than 1, it means they're going to go slower than normal. Okay, so now in order to do that, or one way of doing that is is to use these entities. So so now we're going to we've seen the use of entities for customers before. So how can we carry along their processing time? Well, again, we can subclass the entity, and we can add an attribute called processing. We'll call it processing time. In our model, we'll still call it T sub S, and then just have a getter for that. So if we pass it into the constructor, we don't really need a setter, and for this model, that's all we need. Now for the server, our servers are going to be entities as well, and what they have is they have an efficiency. And again, we're going to have that as a double attribute, a double instance variable in our server. We're going to pass it into the constructor, and then we're going to just have a getter because that's all we need for it. Okay, so now our customers are entities, subclasses, and our server are entities, subclasses. Okay, so now looking at our server component, we now just have a single parameter, and I'm going to make it an array of these server instances. Okay, so that's all we have, and that's all we need, because what else did we have in our multiple server queue model? Well, going back to the first one, we had the number of servers and the service times. We don't need the service times now because the customers are going to come in with it. And we don't need to specify how many servers there are because that's contained in this. We're going to have an array. I'm going to call it all, meaning all the servers. And so that's going to be our parameter. It's going to be an array of server instances, and the size of that array is going to be how many servers we have. Okay, so now our state variables are going to have two containers. Okay, first we're going to have our queue, as we've done before. That's going to be a FIFO container of the waiting customers, that is the customers in the queue, and that's initially going to be empty. But now another state variable is going to be and I'm going to make it a FIFO container of available server entities. So in other words, if a server is available, that means that a server object is going to be in this FIFO container. And its initial state, its initial value, it's going to contain every server in the all array. So the all array has all the servers, and the available servers will initially have all of them. And in a way, this is kind of why this is kind of partly why the definition of the early multiple server queue had the available servers rather than the busy servers. Because it's sort of natural to say, okay, let's start with a container, like here in a more complicated model, we have all the servers in the array, and so those are the ones who are available. So if we collect a time average of the number of this queue container, that will give us the average number in the queue. the time average of the container M, the available server entities, that's going to give us the time average of the available servers, and then 1 minus that over the number is going to give the average one. But in this case, it turns out that rather than do that, we can actually compute the utilization of every individual server separately, instead of just the average utilization overall. Now, just on top of it, because we have a delay in queue and time in system that we can collect. Okay, but the main two, we don't necessarily need those, but the main two for making the model work are the Q and M. Okay, so here's the event graph for that, and again, structurally, it should look very familiar. So let's take a look at that. Okay, so first of all, we have a run, and we have two scalar state variables, D and W. We're going to start off with the NaN because those are transient state variables. You know, they kind of pop up and then disappear. And those are typically NaN. Now, for the Q and M, for the number, for the queue of customers and the available servers, we're going to start by clearing that. And at the first time we run it, it isn't really necessary, but part of the reason for all this initialization here is that when we get to be running multiple replications, which is what is necessary to do production runs, serious analysis, we need to make sure we start in a pristine state. So we're going to clear everything out. So this guarantees that the queue at least is going to be clear. That's fine. But we're going to clear out any lingering servers, but then we got to put them back in. So how can we put them back in? Well, with our init for loop business. So we schedule init with 0, and then one by one, see what we're doing here? We're taking the ith elements of this all array, which was our one parameter, and we're adding it to our available servers container. And then now our upper limit is the length of this all array. And so as long as there's another server to add, we keep adding that. So after all this init, all this init stuff, the available servers container now contains all of the server instances. Okay, is the initialization business clear? Okay. So now let's look at our basic event graph. And if you look at it structurally, it looks very similar to what we had. You know, we've seen this pattern, this, you know, 3 events, one event kind of leads into, schedules another event in the middle event schedules the one in the end, which could schedule the one in the middle again. Okay, that this is a, if you haven't recognized by now, this is a very common pattern, and this is kind of what queuing typically looks like in event graphs. So let's look at this here. So we have an argument on arrival, and that's going to be our customer. And just as we've done before, we're going to stamp their time and add them to the queue. All right, so now see, remember in the past, we've had the condition S bigger than 0, but we don't have an S here. So what's the corresponding thing to S bigger than 0? Well, that the container M is not empty. So if the container M is not empty, that means there's at least one server object in that. So that we can't do this because we don't have an S. But if this is not empty, then there's at least one server object in that container M.
Arnie, I have a question.
Sure.
So you have the init going there. Once it adds all the M, then arrival will just automatically start. There's no
No, no,
scheduling.
no. Oh, how would arrival, okay, looking at just this, how would arrival start?
I would think there's a listener somewhere, but I was looking through the slides and I mean, I guess it's down on the bottom. It just wasn't
Right, yeah, so,
totally
yeah,
clear.
and I would encourage you not to, I mean, I sort of, that line of thought is going to be distracting. I mean, if that's what, I mean, I'm reacting to saying that arrival automatically happens. Nothing, the only thing that automatically happens is the run event. That is the only thing.
Okay. Yeah. So I just wondered, like, if once arrival has something and then the not empty, once that is true, our arrival would then start.
No, no. Well, looking at this, you know, where does that? How does an event occur in an event graph?
Either run or scheduling edge, or
Yeah, yeah, exactly. In other words, run is the only one that just happens automatically. Everything else has to be explicitly scheduled. The only way that this arrival event can occur is if somebody schedules it. And in this component, nobody is scheduling it. So again, the modifier automatic only applies to the run event. That is the only thing that happens automatically. Everything else has to be explicitly scheduled. Now, in this case, as we have been doing for a number of components, when you have this isn't going to do anything until this arrival event gets triggered. And the way we've been doing that is with a listener. So, but what I'm encouraging here is that when building this component, apply the programming virtue of that's not my job. In other words, it is not the job of this component to worry about how this arrival event is going to happen. It's going to be somebody else's job. So while we're trying to, you know, if I'm building this component, if I'm designing it, then I say, okay, somebody's going to schedule an arrival and they're going to pass me a customer as an argument. But I'm not going to worry about that because that's not my job. It's not my job to create the customers. It's just my job to process the customers once I get them.
Then why would you have the run and init inside this component? Wouldn't that be separate as well?
Well, it has to be inside the component because I'm initializing my state variable, and the state variable is inside. Every state variable is completely encapsulated by the component. I mean, in other words, no outside component can change the value of a state variable. Just like in a Java class, remember that our state variables have getters but no setters. And so any other component cannot change this value. This value can only be changed by this component. And so the run event is responsible for two things. One is initializing all of its state variables. So even if we didn't have this init thing, we would still need the run to initialize these two state variables. Just as we did with the multiple server queue. If you remember, we just had Q and S and run initialized those. And again, the thing to remember is the only thing that happens automatically is the run event. That is the only thing. Everything else has to be explicitly done. Okay, is that clear? I hope.
Yeah, I think so. So when this turns on the run and go, it would initialize everything and it would just sit there until the listener until it was told by external component to start arrival.
Exactly, exactly. And if this is the only component, in my main class, if I'm running it, then what would happen is run would spin init, and then it would end. That's the only thing that would happen. But that's what it does. I mean, it's a component like, I mean, think of the components in your computer. I mean, if you have a hard drive that's not hooked up to a computer, it has a lot of potential capabilities, but it's just going to sit there until you hook it up, and the computer starts telling it what to do. So that's kind of, that's a loose analogy of what's going on here. Okay, so an arrival, we're gonna have a customer as an argument. We're gonna stamp its time and stick it in the queue. All right, now if this is empty, if this is not empty, then we can schedule start. If it is empty, then nothing happens. Okay, so now let's look at start service. Now see, in the past, for our entity server model, we popped off our customer. We're doing that here too. But now what we need a server object. And so we're going to pop that off this our M guy here. And then now our delay in queue is still our elapsed time. We've done that before. So now we have that available. And so now here's the thing that, well, now let's finally look at the end service. So here's the thing about the end service. We need two arguments here. We always need the server. We need to know which server ended service so we can add them back in to our available servers container. See, so we do need at least the server. Now, the only reason we have our customer as well is because we want to compute the time that they spent in the whole system. And that's the elapsed time since their timestamp back when they arrived. So the current time here, or the elapsed time since their timestamp, which is in the arrival, that's the time they've spent in the whole system. And in order to do that, though, we need to know which customer it was. So that needs to be passed. So when we schedule that, we need to pass both the server and the customer to end service. And again, whenever we have an event that has arguments, when we schedule it, there must be a match between the parameters we pass and the arguments. If there's a mismatch, then it doesn't work. So this absolutely must happen. And then finally, if our queue is empty, we can schedule another start service. Okay, the final piece is, okay, what about the delay between start service and end service? That is, how long is it going to take to serve this customer? And the answer is, first, we have our processing time of the customer, but then we have the efficiency of our server. So a server with efficiency of 1 is just going to be the processing time. A server with efficiency bigger than 1 is going to take longer. And a server with efficiency less than 1 is going to take less time. So this captures what we were trying to do. That is, the amount of time it takes to process a customer depends on how much work they have to do and how fast the server is in doing it. And again, this is something which matches what we observed presumably in this hypothetical system, where we noticed that some servers were just faster than others. And this model captures that. Okay, so now the customer arrival. So here, this is kind of the simplest way to do this. And this should look fairly straightforward. We've done this a couple times. Conceptually, and again, just to circle back to the question before, if somebody wrote this as part of their event graph, that's perfectly fine. This event graph produces a sequence of arrival events with an argument as a customer.
Sorry, question on the last slide, or I guess kind of all it. We did not have G or TS as a parameter. Should those have been parameter? Are they in all?
Okay, so where did the G and the TS come from?
Yeah, I see them in the UML, but then
Yeah.
we never put them in parameter or state variable unless I guess they're just assumed to be inside of all.
Yeah,
Servers.
I mean, this is part of the definition of our model.
So if it's listed there, we don't have to list them in parameters? I thought we had to put them both.
Well, if it's an attribute of the entity, then it's not a parameter of the model. It's not a parameter of this server component, because each customer is going to have a different one, and each server is going to have a different one. So it's not a parameter. It's not a state variable because they don't change for a given customer. That's just what it is. For a given server, that's what their efficiency is. We're not modeling a server whose efficiency changes over time. But these are TS and G are attributes of the server and the customer. So if I'm defining my model here in the server, I've specified G as its attribute of efficiency, and I've specified T sub S as the customer's processing time. And that means that when I refer to them here, then that's unambiguous. Now, having said that, in the written assignments you've received, you do not need to use any of this. You do not need to use entities at all. Now, if you choose to, there's a way of doing it, but it's not required. You don't need that for the assignment yet. I mean, in future assignments you may need it, but for this upcoming assignment you don't. And again, for the future assignments, if you define what this is and specify what its nomenclature is going to be in the event graph, then you can use it. But you have to now notice the syntax. I can't just kind of use it without anything. I have to use it in the context, in this case, of a customer or the context of a server. So this is the customer's processing time. This is the server's efficiency. Okay, does that answer it? Okay, I'll take silence to be consent. Okay, so back to this. So there are several ways of writing and even implementing this. Let's see, did I put it? Yeah, there's so this is the whole thing. And if you're doing an event graph, this is probably the clearest way to do it. There's absolutely nothing wrong with this. Or you can subclass the arrival process like this. This does exactly the same thing. Only in the code, this is much less typing, because this is the only thing I need to add. In event graphs, this is a whole lot more stuff than this. So which one do you have? They're both correct. If I'm writing an event graph, I might just write this because it's less writing than this. Okay, so let's see. So I didn't, yeah. So right. I didn't write the, okay. So here's how this would work is that I'd have one of these customer arrival guys. I'll call it CA for customer arrival. And then here's my server. Yeah, I should have put this in. I'll add this in and upload an updated copy if you want to keep it there. So here's this is one of these guys, and the server is one of the ones on the previous slide. Okay, so this would be the listener diagram, and we can just do it as a listener diagram because the arrival event here has an argument that's a customer, and the arrival event here, even though it has a different letter, the signature is still a customer. And so this will work. And again, but both of these are correct. And again, this is a little cleaner for just writing the event graph. This is much less typing than in the code. So laziness implies that this is a little lazier to write if you're doing it by hand. Laziness indicates that this is going to be less typing if you're doing it in code. Okay, so let's talk about array states. So when a state, we've seen a little bit of this, and for the next, my next computer assignment actually is going to be a slightly lengthier project, so I'm going to give you more time to do it. I'm still tweaking a little bit just to make sure it's not, to make sure it's as clear as I can make it in terms of what I'm asking you to do, because it's going to involve state variables that are arrays. Basically, it's going to be a model of a transfer line that we talked about. So, but it's going to use entities. So, but that's going to be the code. I will give you the event graph for that. So you don't have to worry about creating the event graph, but you'll be responsible for implementing it. And again, that's going to be the first project. It's going to be worth a bit more. It will take a little bit more. So I'm going to give you some extra time, basically till a week from Friday to do it. But I'm going to try to get it posted by this afternoon. But again, I'm going through it, I'm trying to scrub it to make sure that I'm not being unreasonable, because I know what it is I'm asking you to do. It's different. It may not be what you're hearing me ask you to do. So I'm just trying to make sure I'm as clear as possible about that. Okay, so back to array states. So when it's an array, when you have a state variable that's an array, then typically only one element is going to change at any given event, typically. There are cases where there's more than one, but the most typical ones are when one element of the array changes. And so the state notification, or the property change listener, is, as we've seen, something called an index property change listener. And so what is required is, well, the name of the state still, but now the index of the state that's changed, the new value, and then optionally the old value. And as we've seen with property change listeners, with the firing property change events, there's a 2-argument version, which just has the name and the new value, a 3-argument version that has the name, the old value, and the new value. Now, an index property change, firing an index property change, is we have 3-argument type and a 4-argument type. So the 3-argument type has the index, the name, and the new value. The 4-argument type has the index, the name, the old value, then the new value. So even the order that they're in are a little different than the way they're listed here, but we've seen that. So index property change events are what are useful there. Okay, so here is sort of a kind of a hello world, if you will, example of that. So let's say we want to produce n arrival process like events, meaning each one of them is going to have their own inter-arrival times. And okay, so a parameter, we'd have n, which would be the number of these processes. And now the inter-arrival times, I'm going to need a different one for each one. So my TAI is going to be the inter-arrival time of the ith arrival process. And that's going to go from 0 to n-1 because we have zero-based indexing here. And now my state is going to be also an array. So n sub I is going to be the number of arrivals in the ith arrival process. It's going to start at 0, and I is going to go from 0 to n-1. So in other words, I have two arrays here. One is an array of inter-arrival times, and another is an array of state variables. And this is what that event graph would look like. So basically now we need to kind of initialize each of the arrival processes. So how do we initialize events n times? It's our old for loop. Here now, because we have states here, our run is going to schedule init starting with 0. And every time init occurs, it's going to initialize the ith counter to 0. And then schedule another one, providing that we don't run out, incrementing it by 1. So this piece is all, I mean, we've done this a number of times, but every time init occurs now, it's going to schedule an arrival. And here we're just going to have an I, just the index of the arrival. So we're going to pass that to the arrival. And so now, and once we trigger that, then it's going to schedule the next one. Now it's only passing I, because now the arrival event I, the ith arrival event, is going to schedule the next ith arrival event with an inter-arrival time of t sub a sub I. And every time it happens, we will increment the number, the ith number by 1. So in the implementation, to notify the state change for a single element of the state array, we're going to fire an index property change. And in my notes, I have an implementation example. And since there's only 1 minute left, I don't have the time to do that. So the implementation will have to wait for the next class.